we are ready to study those all-important properties of logarithms. It's these three little properties that make all problems with logarithms possible to solve. It's also what's going to let us solve all those awesome real-world applications that will be coming soon. Now hopefully you'll notice I have started the three properties of logarithms here, and you'll go, oh yeah, I remember these, no problem. Key thing to remember is, what do logarithms represent? And of course, we know, I'm sure everyone out there in video land is saying logarithms represent exponents. So when you think of these properties, you have to think in terms of exponents. If each of those logarithms in this first property are exponents, that means I'm taking an exponent plus an exponent. When we're working with real exponents, do we actually add our exponents? Well, that's in the case of when we're doing something like x cubed times x to the fifth. We add our exponent, we get x to the eighth. So multiplication causes us to add our exponents. Consequently, this property says then that I can multiply m times n. Since I'm actually doing addition, that's really the same process as multiplication. Adding exponents means I'm actually multiplying the entire exponential expression. Okay, consequently, if I have log minus a log, if adding was multiplication, then of course subtracting must be division. Of course, it's the positive one on top, the negative one on bottom. Finally, probably the most important property of logarithms of all time, and that is our property that says, what do you do with a log that has an argument raised to a power? In this case, m to the p power. And I'm sure many of you out there are shouting, plug, 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 because yes, indeed, this is the all-important plug rule that says I can take that exponent, that power on the log, and I can throw it down front, hence spelling plug. So you can take a power, an exponent, and pull it down front to actually work with it. Okay. Our entire assignment today is my attempt to beat you to death with how do you work these logarithm properties. So we're going to do numerous problems using only these three properties. You'll notice here, first one I have up, we have a log base 7 of x plus 5 plus a log base 7 of x minus 3 equals 2 times the log base 7 of 3. You will note that they all have base 7s. I will not be mean to you and be giving you problems where you have different bases in the same problem. So in this case, what do we do when we have a log plus a log? We actually know that addition in logarithms means multiplication, and so we would FOIL that together. Now, our goal is to get it down to one logarithm on each side of the equal sign. Okay, but I need it to be log base 7 of some quantity called the argument on each side. I cannot, in the case of the right-hand side, I can't have this 2 in front of it. So where am I allowed to move that 2 to get it out from in front? And of course the answer is I can bring it up, actually reversing the plug rule. I can bring it up and move it to be the exponent on the 3. The whole idea is just like when we were making common bases to solve our exponential equations. In this case, we're trying to get logs with a common base on each side. Because if we have the same logarithm with the same base, then I know I can actually set their arguments, or those inside expressions, equal to each other. Now that I have done that, it's ordinary solving, and this is your typical quadratic. So I'm going to subtract 9 over, which is going to give me negative 24, set it equals 0, and we've solved many a quadratic in these days. 24 has many possible factors, though. Since it's negative 24, I know I'm going to have opposite signs, and so that means I need two numbers whose difference is 2. That's going to get me 6 and 4, which will give me a plus 6 and a minus 4. Consequently, I have solutions then of negative 6 and positive 4. But wait, you're not done yet. If you'll recall, when we did the domains of our logarithms, on logarithms, the domains have to contain positive values. So every time you work a problem that can start it out with logs, you have to verify that these solutions will indeed give you positive values. So I have to take negative 6 here, put it up in this quantity. Will negative 6 plus 5, I'm looking back at the original equation, will negative 6 plus 5 actually give me a log of a positive number? And the answer would be no. So I can't have negative 6. You cannot have the logarithm of a negative number. Same thing goes with 4. If I put 4 in that same expression, is 4 plus 5 going to be positive? Answer, yes. Go to the next place you see an x. Will 4 minus 3 be positive? Yes, it will. So consequently then, 4 is our only solution. So you have to check with positive values inside a logarithm. Finally, our next example here, you notice I'm using natural logarithms. It makes absolutely no difference whether you use common logs, natural logs, base 50,000 logs. These properties apply regardless of what type of logarithm you're using. The key thing is that we're using the same type of logarithm across the problem. So since these are all natural logs, it's fine. Now some people are bothered on this one by the fact that I have a natural log plus another log, and then I also have a subtraction. Are you allowed to have 3 things in one problem? And the answer is sure. And you're also allowed to deal with all 3 of them at once. So our properties say when I have a log plus a log, what am I supposed to do with those quantities? Well, addition means multiply. So I'm going to take 4x times 3. But since it's also minus a natural log of 6, the subtraction means division. So I'm actually going to just put the divided by 6 on the bottom. You can take care of all 3 pieces at one time. On the right-hand side, are we content with 3 times the natural log of 4? The answer, of course, is no. We can't have that coefficient of 3 in front. So we're going to reverse the log rule and put the 3 up as the exponent. Now I can see that I have both natural logs on each side. So since they are the same log, I can now set their arguments or interior portions equal. This first one is actually 12x over 6, so that would reduce down to 2x. The right-hand side, 4 cubed, is 64. So I really have 2x equals 64, which means x equals 32. Now you still have to check. That's always important. In this case, there was only an x in one position here, so if I put 32 in that 4x, will it be a positive value? Of course it will. So that means 32 is an acceptable answer. Well, you'll notice all these problems I've done so far, we had logs on both sides of the equal sign. Well, we're going to change that now. What happens when you don't have logs on both sides of the equal sign? In this case, I have a log of x plus a log of x plus 3. Notice that x is written a little funny there. Let me fix that. It is not, the x is not a subscript. The x is the argument. Okay, you're going to proceed to solve these at first like usual. You have to get it down to one logarithm. You can't have log plus a log minus a log. So our property here would say, yes, I need to multiply, which would give me x squared plus 3x. But here's the monster distinction, just like monster brackets. So if I have x squared plus 3x, I can't say it equals 1 because it's not a log on both sides. And from your assignment you just did, what did you do every time there was a log on only one side of the equal sign? Somebody out there is chanting it. Yes, indeed. You changed it to exponential form. And we will do so again. Every time you see a log on one side, you're changing to exponential form. So here's the question. What's the base? How do I go to exponential form when this log has no base on it? Well, of course, you're saying, but it has a base 10. It's a common log. So when I go to exponential form, I can say I have base 10 to what power? What you're equal to is always the exponent, so I have 10 to the first power equals x squared plus 3x. Now I can set it equal to 0 and proceed to solve like a normal quadratic. That's going to factor as x plus 5 and x minus 2, so I'm going to get answers of -5 and 2. Am I done? Absolutely not. I have to check my answers, and I have to check in the original problem. So if I was to sub -5 up there, I'd have the log of -5. Well, that's not allowed. Can't have a log of a negative number. If I put 2 in there, that's good. If I come over to the second expression, 2 plus 3 would make 5. That's good. So 2 is a possible answer. Now I want to emphasize that not all negative answers are bad, and not all positive answers are good. For example, in this case, if, say the expression up there had been 2 minus x, if I'd stuck -5 in there, 2 minus -5 would make a very nice positive number. So you cannot assume all negative numbers fail and that all positive numbers work. In some instances, the positive numbers fail. So you must check, and you must check in every quantity containing an x. Now the other thing I want to show you here, well, actually I think I'll come back. Hold on to that a second. Let me do the natural log one first, and then I will come back and show you an alternative method you could have used to solve that. But first let's work the one with the natural log, because I think it'll make it easier to see what's going on. So in this case, same old problem. You're sort of like, well, why is she doing another problem? This isn't any different. It's 2 logs. We got a 3 on the other side, which doesn't have a log. So I'm going to have to do something different here. Whoops, wrong color. Let's not do that. And what do I do when I have a natural log minus a natural log? Subtraction in logs is division, so this would give me x plus 2 divided by 4 is equal to 3. Well, as you may recall, when you have natural logarithms, there's usually an easier way to deal with it. Yes, we could change this to exponential form. It's the same thing I'm about to do, but this other method seems to stick better. What can I do to get rid of a natural log? And of course your answer is, well, you use e. But the question is, how do I have to place them so that e and natural log actually make each other cancel out? Since I have a natural log, I can't go sticking e on the inside of it. But what I can do is I'm allowed, and once again, I'm only allowed to do this because I'm doing it to both sides of the equal sign. I can put an e underneath each one of these, and so I'm actually raising this up to be e to the natural log of x plus 2 over 4 power, and e cubed. Now, because I have an exponential function e raised to a natural log power, they still do cancel each other out, and I'm left with x plus 2 over 4 equals e cubed. Now, I need to multiply the 4 to the other side, so I would go make that a 4e cubed when I multiply it to the other side. Write that in there so you can see that. And then last but not least, I would have to subtract the 2. Okay, if they ask for an exact answer, you're going to get 4e cubed minus 2. However, most of the time, they prefer that you go to a decimal equivalent. So you're going to have to punch that in the calculator, which I am doing at the moment. I don't, for some reason, seem to have that one worked out. So 4e cubed minus 2. And we would get approximately 78.34. Do I have to check my answer? And the response would be yes, I do. I still have to make sure that that number will give me positive value. So if I go back to the top problem and I put 78.34 in for x, will it maintain a log of a positive number? And yes, it does. So that is indeed an acceptable answer. So anytime you want to get rid of natural logs, you can just use e's on both sides. Okay, what I want to show you now that we've done that, I want to show you an alternative for how you could have solved the above problem. And that pink is just not going to show up good enough. Let's go this way. On the above problem, once we got it down to logs on each side, if I had gotten it down to this log of x squared plus 3x equals 1, your alternative method for solving that, rather than changing to exponential form, it's actually going to result in the exact same thing here, is to do what we just did with the e's. With e's, I put an e under both sides. So here, if I want to, since this is a base 10 log, if I wanted to get rid of that log, I could put a 10 under both sides. So I would have 10 of a common log x squared plus 3x equals 10 to the first. So I could put the same base under both of them. Here on the left side, an exponential function base 10, a log base 10, they cancel out, so I would still end up with x squared plus 3x equals 10, which is the same thing I had up above. So if you like that better with always putting a number e underneath each side, if that seems more logical to you than going to exponential form, go for it. You get the exact same result. Whatever works best for you and processes in your brain is what we want to do. Okay. That concludes our fun and excitement for today's problems. We're going to solve some fun and exciting exponential equations next time. Practice hard on those logs. Do every problem until you are sure you have these methods ingrained in your head. Good luck.